Alright, I'm going to go through question number 5 on the 2017 fall final exam for practice. This is an important question to understand for our upcoming final exam. Okay, so if it's degree 3, then it has to have 3 zeros. So we have 1, 2 zeros. So we need a third zero, which is not too difficult because imaginary or complex zeros come in conjugate pairs. So if one of our zeros is 1 minus 4i, we have another zero that's 1 plus 4i. So a conjugate pair would have the same number at the front, and then the imaginary part, one would be positive and one negative. Okay, now we take our 3 zeros and we turn them into factors. So our negative 3 turns into x plus 3, and our 1 minus 4i turns into x minus 1 plus 4i, because the subtraction of the 0 would distribute. And then the factor for this 0 would be x minus 1 plus, oops, of course I had to mess up, x minus 1 minus 4i. Now here's the thing, if you forget to distribute the fact that you're subtracting the 0 from x, like if you were to do x minus 1 plus 4i for this one, and x minus 1 minus 4i for this one, and not distribute that negative, it really wouldn't be a big deal because you just have to have both of them in the problem. The place where I see people make mistakes is right here. They try switching these signs, like make one of these positive and one of these negative because they make this negative instead of that positive or something like that. So just be very cautious that your real terms are staying the same, and then this will be the opposite of those, and then your imaginary terms are opposites, so you have one of each. Hopefully that makes sense. Alright, so to find this polynomial function that's not in factored form, that's what the question specifically says, it means we need to multiply everything out. Instead of multiplying this times this first, this real 0 times this imaginary 0, I'm going to multiply the two imaginary zeros together first because the imaginary stuff will cancel out. So x times x is x squared. X times negative 1 is negative x. X times negative 4i is negative 4xi. And then let's move on to the next term. Negative 1 times x is negative x. Negative 1 times negative 1 is positive 1. Negative 1 times negative 4i is positive 4i. Last, I'm just going to go with a different color so I don't mix up where I am. 4i times x is positive 4xi. 4i times negative 1 is negative 4i. Be very careful of your signs. One little mistake gives you the wrong answer. So 4i and negative 4i would be negative 16i squared. Now about I squared, since I is the square root of negative 1, I squared equals negative 1. That's how our imaginary numbers can become real numbers. So if I squared is negative 1, then this negative 16i squared actually is a positive 16. Alright, let's combine like terms. We only have one x squared, so I'm going to write that down. So here's my polynomial function. I have this x and this x, so that'll be negative 2x. Now here is a beautiful bonus in this situation. This negative 4xi and positive 4xi cancel each other out, because one's positive and one's negative. That happens again here. Positive 4i, negative 4i cancel each other out. So all we have left is this 1, and what used to be a negative 16i squared is a positive 16, so we just add those together, and that turns into 17. Now, is this our final answer? No. That is just the quadratic that comes from multiplying these two factors together. And in fact, if you had time and wanted to check this, you could use quadratic formula to solve it and see if your answers are these two imaginary numbers, because they should be. Alright, next, let's multiply this times our real 0 factor. Multiply this out again. So x squared times x is x cubed. X squared times 3 is 3x squared. Negative 2x times x is negative 2x squared. Negative 2x times 3 is negative 6x. 17 times x is 17x. And 17 times 3, oh boy, I think that's 51. Hopefully I'm doing that math correctly. So now we combine like terms, x cubed plus x squared plus 11x, because I'm combining my negative 6 and my positive 17x together, plus 51. Here's my polynomial function, not in factor form, rather in general form. And checking our answer key, it looks like I have obtained the correct answer.